Okay, and our next speaker is Dakshita Karana from the University of Illinois at Urbana-Champaign, and she will be speaking about her project that is focused on secure federated learning for clinical informatics with applications to the COVID-19 pandemic.
Hi, it's a pleasure to be here. Thank you for supporting our project. Okay, so this work is about performing secure federated learning in order to perform collaborative diagnostics over distributed hospital databases, and we wanted to tailor this research specifically to the COVID-19 pandemic. This is joint work. What I'm going to be presenting is a project that we have jointly with PI Sadmi Coelho, co-PI William Bond, and we also have fantastic project managers and a set of great students working on this. I also want to really thank my collaborators, Sanmi, Nishan, George, and Chris, for letting me borrow some of their slides when preparing this talk. So the setting that we're interested in is the following. We have many different hospitals spread across different corners of the world, individually, making use of the power of machine learning to train diagnostic models on their local data. Now, wouldn't it be wonderful if these hospitals could actually collaborate with each other in real time to make use of insights that can be derived from each other's data in order to improve their own models? Of course, they cannot blatantly share their data with each other because of privacy concerns. Nevertheless, despite this situation, it turns out that there's a lot that can be done. So our starting point in enabling this type of collaboration between hospitals is an approach called federated learning. This was first introduced in the context of mobile networks, and the idea was to enable a central server, like one at Google, to train models on the joint data of millions of mobile phones while still preserving the privacy of every individual person. That is, the server would only learn aggregated updates that would provably reveal little to no information about any individual data point or any small group of data points. And now our approach is to actually apply federated learning, bolster it with secure protocols, and find a way to use it to perform better medical decision making. So to do this, we combine expertise in federated learning and machine learning with what is called secure computation, which allows for the design of protocols that enable many different participants to collaboratively compute functions on their private data without having to reveal any of this data to each other. And so we combine these two with expertise in medical decision making and specifically with applications to COVID relevant clinical predictions. Our goal is to develop a computational protocol to securely train machine learning models on data that is distributed over several different establishments. The idea is to have all these local sites update their model parameters via information that is obtained from a central server without the need for any of these local sites to share their data in the clear with the server, and without the need for the server to transmit information about these local sites to each other. So the idea is that in this setting, neither the server nor any of the local sites nor any subset of possibly colluding sites should be able to learn more information about the private patient data of any other hospital than what is revealed to them by some aggregated statistic. Our vision is to use this to improve healthcare quality and patient safety through the combined efforts of clinicians and researchers. And what we want to do is enable private training of these models on these pooled data sets. In the longer term, we want to open source these techniques. Once we have these protocols developed and some initial implementations, we want to open source these techniques and apply them to other diagnostic applications, even beyond COVID. And the idea is that obtaining insights from data that is held by different hospitals will enable healthcare providers to respond faster and learn more than they would have had they concentrated on data that is locally stored at their private servers. And the aim is to use this to enable medical breakthroughs via privacy-adherent computations on extremely large-scale clinical data that possibly involves data from all corners of the world. So as a starting point, we tried to plot ROC curves on public COVID data sources and Chexpert data, and this is without collaborative diagnostics. And we obtained some preliminary results that I show here. But what we really want to do is use our techniques to train with distributed data and not data that is held on any single server. This leads to many different challenges, some of which I have listed here. Two of the most important ones are the first, that local data held by different servers comes from different types of populations. So it is very unbalanced, and because the demographics are different, there are many characteristics that are very different. And so models that train collaboratively on these types of unbalanced data have to keep in mind the fact that these come from different demographics and are not IID, which is typically a common assumption when building machine learning models. The second challenge is security, which means when we have many such participants, like I said, it is important to ensure that data of one hospital is not shared in the clear with the other, because that would violate all sorts of privacy laws. And then some other challenges are more relevant to task scheduling and other types of systems issues that come up, including errors and communication dropout. So those are, so I'm in this talk, I'm going to focus on how we address the first two challenges. The first challenge that I just told you about is population differences in data sites can actually confuse the model. And this could lead to unfortunate settings where it is not clear whether it is any better to have a global model or any better to train to even use insights from others than just locally training on your own data. So there's a cartoon explanation here where Dr. A asks, I'd like to focus on only local patient demographics. And Dr. B says, but you might have less data and misinformation, and especially with new diseases like COVID, it is very important to have quick real-time information. And at any local site, one can only have so much information. And so the goal is to have to understand what types of settings are more amenable to federated learning when many different hospitals are trying to combine their data. And towards understanding this, we have ongoing research where we try to understand what are the types of settings where building a single global model that then helps local models and offers insights and allows local models to actually retrain themselves is better than having a single local model operating at each individual data site. The second challenge, like I said, is about privacy of patient data. Sorry, let me see, I'm halfway through. The second challenge is to ensure privacy of patient data while enabling these types of collaborations. To do this, we rely on a classic cryptographic technique that's called security via multi-party computation. So in this setting, imagine more generally any set of parties that have their secret data. I'm calling it X1, X2, and X3 here. And they have a general function F that they want to compute on this data. The goal is for all the parties to be able to recover F applied to X1, X2, X3, so forth at the end of this protocol. And throughout this process, no one else should learn anything about, no one participant in the protocol should learn anything about the data held by any other player, except for the outcome of the function, which is denoted by F applied to these inputs. A really simplified cartoon version of this problem is called the YAOS Millionaire problem. And so imagine there's two millionaires. Alice has X1 million dollars and Bob has X2 million dollars, and they want to compute who out of them is richer. So this is one of the first historic um, um, references that studied this problem. And the aim was to design a protocol where both Alice and Bob talk to each other. At the end of that, they learn who is richer, but no one learns anything else about exactly how many $1,000,000 the other person has in their bank account. Now, this can be generalized way beyond millionaires to computing any arbitrary function on private inputs held by two players in such a way that both players learn the output of the function and no one learns anything else. And now the goals are one, correctness, which means parties should learn the right output of the function at the end of the protocol, and security, which says that as long as players follow all the protocol steps like they were asked to, no one should learn any extra information. And one can ask for an even more enhanced version of security where there are adversarial players involved who arbitrarily deviate from protocol specifications and try to actively cheat in such a way as to gather too much information, information. So for now, our focus in this project is on this simpler setting where we just assume everybody follows protocol execution. And in that setting, can we ensure that patient data is not revealed and at the same time have a protocol that allows hospitals to actually learn outputs that they can use to improve their own local models. So just some additional notes. We don't care about what can be learned from the output of the function at the moment because we assume that the functions are large aggregation functions that are aggregating a lot of data over many different sites. So the aggregate data, we assume for now, does not reveal too much information about any individual patient. Of course, this is a strong assumption, and there is an orthogonal body of literature on how to eliminate this assumption and get an even better privacy guarantee. And this is called differential privacy. And one of the nice things about what we are doing is that it can be combined very easily with techniques from differential privacy to get these stronger guarantees. But for now, again, we just assume that the function output reveals no information about any small enough set of patients. The second thing that I want to emphasize is that this is an interactive protocol, which means the parties need to communicate back and forth. And one active line of research that we are engaging in is to understand exactly how much communication overhead do these privacy issues lead to in this setting. I also want to point out that there's a rich literature in this area of multi-party computation. The theory of this area has been developed for 40 years now, and it's been coming into practice more in the last decade or so. And so we're using some of those practical protocols and trying to understand how to apply them to this setting of hospital data. So I want to, in the last, I guess I have 5 more minutes, so I want to say a little bit more about the concrete ideas that we are developing. So first off, I want to start with some very simple ideas. Suppose we have three hospitals. I've denoted them by mobile phones here just to emphasize that they're individual clients. And suppose we have one giant server that's in charge of aggregating all this data. And we want to aggregate this data in a privacy preserving way. That is, the server must learn the sum of x1, x2, and n3, and only learn the sum and no other information about what these individual values x1, x2, and x3 are. It turns out that this type of functionality already allows you to compute things like mean, which is one of the key steps in performing machine learning in the federated setting. So it turns out that if one can compute the aggregation functionality securely, then that can be used to bootstrap directly to secure federated learning. So now zooming into the aggregation functionality, the first very simple idea is the following. Suppose we have these 3 players with their secret inputs sample sets of noise that cancel each other out. So for example, zooming in on the blue triangles, suppose the first player samples noise, let's call that N1, and the second player samples noise that's minus N1. So these 2 blue triangles, again, denote something that just cancels each other out. Similarly, the second and third player sample noise and the first and third player sample noise. And now they add their noise to their actual inputs and send the result over to the server. That is, the first player adds the noise N1 and let's say N2 to their input X1 and sends the result over to the server. Similarly, the second one and the third one. And these noise values have been picked out in such a way that they cancel each other out. So at the end of this, the server just ends up with the sum x1 plus x2 plus x3. And moreover, as you can see, no individual value, neither x1 nor x2 nor x3 were revealed to the server in this process. I'm sorry, this last value that the third client sends should be x3 plus orange triangle plus green triangle. So now this looks simple enough, but when actually trying to implement it, there's some issues that come up. First off, in this setting, because of some technical reasons, we need in order to ensure good privacy, we need to make sure that we sample the noise from the right space. And it turns out the best way to do that is to make sure that x1, x2, and x3 are all integer values. And now this is not very, this does not fit very well with what machine learning models have, which are actually floating point values. So we need to perform these conversions, which leads to a little bit of a loss in accuracy. And again, one of our research challenges has been to just understand how much loss do we need to endure in order to have a system that works reasonably fast. The second challenge that comes up is that each of these noise values needs to be randomly generated at every epoch of the training process, and then synced with the noise value of the other player that needs to cancel this out. So basically, we need for every pair of hospitals involved, they need to generate noise values at every time step in such a way that their noise values will cancel each other out. And it turns out, again, this is more non-trivial than it would appear to be, because generating random noise is actually expensive. So we rely on cryptographic objects called pseudo-random generators to ensure that this noise is generated at every step efficiently without the need for hospitals to have to talk to each other and coordinate each time. So with these initial ideas in place, we implemented our system on an MNIST sample dataset, and we got and I've plotted here, and we've plotted here trade-offs on the number of bits versus accuracy. And you can think of this as like the extra computation and communication that needs to go in for a given amount of accuracy in the model. So some of the next steps that we want to look at is, first off, we want to understand how to aggregate robustly. The reason is the following. It turns out that robust global models, along with fine-tuning, outperforms both standard federated learning and local models. The reason is the following. Remember, we said that it's not clear whether learning from other data is beneficial or not. And one of the reasons that this is not clear is because data from a different hospital could have many outliers in it. And once you have those outliers, that could mess up the parameters. And it may turn out that just locally training on your own data is just a better idea. But it turns out that once you can have a good mechanism to remove these outliers, then indeed federated learning with robustness is much better than standard federated learning or local learning. And so what we want to implement is secure, robust federated learning. In order to do this, we've laid out a sequence of steps, but I think I'm out of time, so I'm going to skip over this part and just conclude. So our status at the moment is that we've completed basic software and infrastructure and technical research. We've implemented our ideas, the ideas that I told you about so far, into a basic infrastructure that can actually be run now on hospital data. We're still in the process of getting the right data, and so far we've been running it on data that we've obtained from the internet. We also have other modeling and testing in progress. We're trying to understand all edge cases where implementing federated learning would end up being worse than training on local data. And in some ongoing research, we're trying to bring down the computational costs of security in the setting of robust federated learning. And this is a completely new area where there has hardly been any research on trying to understand how to do robustness and security at the same time. And so we're also in discussions with some additional clinical partners. So in addition to our collaborators at OSF, we're talking to other clinical partners. And the idea is that we would like to get as much data as possible with strong privacy guarantees, so we can actually evaluate how much better it is to have data from all over the world versus your own private data. That brings me to the end of the presentation. Thank you so much for, again, for supporting this endeavor. Yep.
Great.
Thanks.
Thanks very much, Dakshita.